Well, now we are going to discuss the next part of electromagnetic induction, and this part is mainly related to mutual induction. Now, in mutual induction and mutual inductance, these are two different things. Mutual induction is basically a concept, whereas mutual inductance is a constant of that circuit in which the induced EMF is induced. Now, what we have to do in the mutual induction, we have to consider two basic circuits. One is the primary circuit and other is the secondary one. Like in the figure, we are finding that in the primary coil, a key is adjusted along with battery and rheostat. The purpose of the rheostat is to vary the current by changing the resistance. Now, the moment we press the key, the circuit will be complete, that is, the switch will be on. We find that current will flow in the primary coil. This current will give rise to magnetic field, and this magnetic field will give rise to magnetic lines of forces, which will be associated with the secondary coil. The moment flux is associated with the secondary coil, the EMF will be induced in the secondary coil. This induced EMF will give rise to induced current, and galvanometer will start indicating deflection. So now in the context, on changing the current in one coil, if the magnetic flux linked with the second coil changes as a result of EMF is induced in that coil, then this phenomena is called mutual induction. We can further increase to the concept that when the circuit is on in the primary, the EMF is induced in the secondary, and when the circuit is open in the primary coil, after induced EMF is produced in the secondary, we find that due to that induced EMF in the secondary, when the circuit is open in primary, the another induced EMF will produce in the primary coil. So there will be momentary generation of current in the primary coil the moment we open the circuit. Now the coil in which current is allowed to flow, that is called primary coil, and what we find is that the secondary coil, the induced EMF will be generated because of the change in flux. So A and B are the primary and the secondary coils respectively. Now, with respect to time, first of all, we consider coil A. In coil A, when current is passed, that is, circuit is closed, we find that flux is linked with coil B, and due to this, the flux will be generated in second coil. M is the mutual inductance of the second coil. The phenomena by changing the current in the first coil and inducing the current in the second one is called mutual induction, and M represents, that is, the coefficient of mutual inductance or simply mutual inductance. Now, if current in the primary coil is 1 ampere, then flux in the second coil, that is B, that will be M. So, coefficient of mutual induction is basically the flux produced in second coil. Thus, the mutual inductance between the two coils linked magnetically is numerically equal to magnetic flux linked with the secondary when the unit current flows in the primary coil. Well, the unit current means 1 ampere current is flowing in the primary coil. The EMF induced in the secondary according to the Faraday's and Lenz's law. So, in the equation we are finding in the coil B, EMF is induced, and this is given by minus d phi b by dt, and this is obeying the Lenz's law. The Lenz's law is basically indicating the direction. So the improvement of the Faraday's law, because in the Faraday's law there is no direction, whereas Lenz's law gives the direction. So according to Lenz's law, the direction of the induced EMF is such that it opposes the cause which produces it. That's why a negative sign is indicated in the equation. So EB is equal to minus d phi b by dt, and that is equal to minus m dia over dt, where phi b is the flux generated in the second coil. Now, we can estimate the value of the mutual inductance by using the formula, that is EB over minus DIA divided by dt. This can be briefed as EMF induced in secondary divided by rate of decrease of current in primary. Now, negative sign we can remove by taking the modulus. So, wherever the calculations are to be made, we have to take the modulus of the number. However, in the equation, minus dIA over dt is obeying the Lenz's law, and it is equal to 1 ampere. Then M will be equal to EB. Therefore, the mutual inductance between the two coils is numerically equal to EMF induced in the secondary coil when the current in the primary coil changes at the rate of 1 ampere per second. Ampere is amps unit of current or SI unit of current. Now, the unit of M is discussed in amps system. The units of M will be taken as Henry or Weber per ampere. 1 Henry and 1 Weber per ampere are numerically the same. So, mutual inductance is estimated by function EB over minus DIA divided by dt, and that will be 5B over IA. Now, in order to have the dimensions of magnetic mutual, that is mutual induction, or the dimensions of mutual inductance, we use the formula 1 Henry is equal to 1 Weber over 1 ampere. So, by computing the dimensions of Weber, well, you will remember Weber can be estimated by function phi is equal to BA cos theta. So, by using these dimensions, we will come to a conclusion, that is joule per ampere square. The joule will be the product of Newton and meter. So, for Newton, we have to put the dimensions of force. MLT minus 2 into meter means L and ampere square means A square. By calculating, the net dimension comes to be ML2 T minus 2 A minus 2. Now, mutual inductance between the two coils or between the coils depends upon the number of turns in the coil. So, now this fact we have to explain in terms of N1 and N2. That is, if we consider two coils, N1 will be the number of turns in the primary coil and N2 will be the number of turns in the secondary coil. So, mutual inductance between the coils depends upon the number of turns in the coil. Area and permeability of the core. Normally, core is made up of soft iron placed inside the coils, and permeability means the power of conduction of magnetic lines of forces depending upon magnetic properties of material. The magnetic properties can be ferromagnetic, the paramagnetic, the diamagnetic. The permeability of ferromagnetic is greater than that of paramagnetic, and that of paramagnetic is greater than that of diamagnetic. Diamagnetic substances have negative permeabilities. Therefore, we find that diamagnetic substances are repelled by the magnet. Similarly, for the paramagnetic substances, we find that their permeabilities are between 0 and 1, and they are feebly attracted by the magnet. Similarly, the ferromagnetic substances, they are strongly attracted by the magnets. This property exists in iron, cobalt, and nickel. The paramagnetic substances are generally, that is, platinum, manganese, oxygen, whereas diamagnetic substances are generally arsenic, or it will be water molecules, so they have got the negative permeabilities. The core is made up of soft iron, because for soft iron the susceptibility is more. Susceptibility is the property due to which the material gets magnetism easily and loses magnetism easily. So this core is placed inside the coil. Larger is the magnitude of M, more is the EMF induced in the secondary coil. Out of the two coils coupled magnetically, one coil can be taken as primary and other coil can be taken as secondary. Therefore, mutual induction can be given as MAB and equal to MBA. When we write AB and BA, it means the sense of keeping a inductor is in the opposite sense, and both will be equal to M. Mutual inductance between the two coaxial solenoids. When we speak coaxial solenoids, their axes are same and the length is taken as L, cross-sectional area is A. In that case, the coefficient of mutual induction M can be calculated by formula mu naught N1 N2 into A over L. N1 and N2 are the number of turns in the primary and secondary coils. Mu naught is the absolute permeability of the medium where the coaxial solenoids are kept. L is the length and A is the area of coil. If medium is not specified, then it means that the coaxial solenoid is kept in air medium or in vacuum. In that case, mu naught can be taken as 4 pi 10 to the power minus 7 Henry per meter or Weber per ampere meter. If two coils are wound one over the other, then mutual inductance will be maximum. And the value of this maximum mutual induction can be calculated by function M is equal to K L1 L2 under root. K is the constant of coupling. So it is coupling constant. K is a coupling constant of the coils and its value varies from 0 to 1. Now we can see the figure. In the first figure, we find that P and S, they are wounded over each other. And in the second one, we find the coils are parallel. That is, one coil is kept over the other. Either primary can be kept over the secondary or the secondary can be kept over the primary. And similarly, the least value of M will be adopted in case of P and S will be perpendicularly adjusted to each other. So either primary coil is perpendicular to S or secondary coil can be perpendicular to S. So in the case of wounded together, we find that the maximum value of M and the value of M decreases when they are over each other, and when they are at 90 degrees to each other at pi by 2 radians, we find that it will be the least value. Therefore, if K is 0, then there will be no coupling between the coils, that is, magnetic flux produced by the primary coil is not linked with the secondary coil. If K is 1, then both coils are coupled together. There will be maximum transfer of energy or the maximum work is done. That is, magnetic flux produced by the primary coil is totally linked with the secondary coil. If two coils of self-inductance L1 and L2 are coupled in series, such their windings are in the same sense, then the mutual induction or the coefficient of mutual induction M can be estimated by function L is equal to L1 plus L2 plus 2M. Now similarly, if they are coupled together in series and their windings are in the opposite sense, then equivalent inductance will be L is equal to L1 plus L2 minus 2M. So what exactly we have seen? When the coupling is done in the same sense, we have to add 2M, and whenever the coupling is done in the opposite sense, we have to subtract 2M, but L1 and L2 are added together, and either we have to add 2M or we have to subtract 2M depending upon the sense in which the windings are done. If they are done in the same sense, then it means we are adding 2M, but if the coupling is done in the opposite sense, then it means we have to subtract 2M.